Here's another one with the spring. Okay, now this one's a little bit unusual, and in some ways it's simpler. Okay, but in another way it's a little trickier. All right, but let's just take a look at what it is we're searching for. There's a spring. Okay, you can see it in the picture. The block has got a force that's going to pull on it to the right, and the spring's at rest when it's up and down. So at s equals 0, the spring's at rest, and then it gets pulled to the right, and the spring stretches out, which is going to slow it down. You can imagine, okay, or try to slow it down. Determine the acceleration. Okay, so that's our goal right there. Determine the acceleration. And so we're going to start with the forces, and we're going to move to the acceleration, like that. So let's get some labels on here with some forces, and I'm going to do the picture of the block when it's on the right there. So of course there's how many times have I made that mistake? Of course there's some normal force, and there's a weight there. Okay, then the spring force is pulling back here. Okay, so there's Fs, just like this. And of course, obviously the 100 is here, but there's no friction involved in this thing. Okay, there's no friction. Now let's go ahead and do our free body diagram. Like so. Okay, so we've got the 100 here, a normal force, and then we're going to have the weight down here, mg. Okay, now my spring force, I think what I'm going to do is I'm going to do it like this. We're going to go ahead and put it in components. Let's say spring force X, and let's call this spring force Y. Okay, so, anyway, I'm going to need it in components anyway. Now let's look at what's happening with the Y components. MAY. All right, so we've got the normal up, the Y component of the spring down, and the weight down, and that's 0. Okay, so if we needed that normal component, we would have the weight plus the vertical component of the spring. Okay, now that vertical component of the spring is going to depend on our angle. All right, so let's talk about that for just a second. So let's suppose we've got some angle here, just like that. Okay, now if that's the case, then that means there's my angle there as, just kidding. That's not my angle. That means here's my angle right there. Okay, and so what we would have then is I want the black color on there. The N is going to be the force of the spring, which is Ks. And then that's going to go as the sine, or sorry, not in this case. It's going to go as the cosine of that angle. Okay? The cosine of that angle. And so what that means is, as this thing is getting pulled to the right, all right, that angle theta is constantly changing. And so that Y component of my spring force is constantly changing. All right, and it's changing with the angle. It's changing because my spring is being stretched. So it turns out to be kind of complicated. All right, now for us, all right, what we know is that we're interested in the point where S is 0.4. So that is kind of helpful, all right, because that means that I've got a triangle 0.3, 0.4, it's a 3, 4, 5. You see that? Okay. And then with the 3, 4, 5, my adjacent is 0.3, my hypotenuse is 0.5, and so that means cosine is actually 3/5 in this case. Okay, at this particular moment. All right, now obviously if S was at 0.2 or 0.7, we'd have to figure out the angle. We'd have to do all that stuff there. Okay, it would be just an extra step in there, but they made it really easy for us here. So that would just be 3/5, which means that then we can call this, say N is W plus 3/5 KS. Okay. Since there's no friction, we don't actually need that. So why did I go through all that? I went through it because I wanted you to see about the cosine of the angle. Okay, I wanted you to see how we deal with that, because we're going to do that again as we do the x component. Okay, so sum of our forces is AX. Okay, look at my free body diagram. I've got 100 minus FSX, and that's my MA. Okay, which is what I'm looking for. Okay, so 100 minus KS. It's going to go as the sine of theta. Okay, but in this case, the sine of theta is 4/5. So we can go 100 minus 4/5 sine theta is equal to MA. Okay. Solving for A, 100 over M minus 4 over 5M KS. Alrighty. There we go. Okay. So you're ready to just plug your numbers in and go with it there. Okay. Remember, S is 0.4, K is 200. Everything's good. Okay. I don't think I have anything else I want to say about that one. There we go. You might kind of think, well, what would be different if we'd had friction on there? Okay. And having some friction, we would have ended up with a minus FK here. Okay, so we would have had to carry that through. Wouldn't have been that bad, really. Okay, especially since we went to all the trouble to get an expression for our normal force. Okay. Anyway, I'm gonna do one more for you in this series. Okay, about pushing blocks. All right, and it's pretty interesting. It's simple, but there's some interesting things to it.